I'm Vaidehi. You might have heard about trees and binary search trees and feel like you're supposed to know about them. Or you might know about them but might be unsure about why you need to know about them. Either way, I want to show you how fascinating trees and binary search trees are. And hopefully, you'll find them as interesting as I do. If you've watched my previous videos on linked lists and stacks and queues, you're already familiar with the idea of linear data structures. Linear data structures are all over the place. They're basically data structures that allow you to contain different elements, but they're always created with some sort of order and sequence in mind. Nonlinear data structures are different in two fundamental ways. First, there's no real concept of an order. There's no idea of a beginning point and an ending point necessarily in any of the nonlinear data structures that you might see. The other fundamental difference is that there is no sequential way to traverse through a nonlinear data structure. Trees and binary search trees are probably one of the most well-known forms of nonlinear data structures. And because they're so fundamentally different, it's important to break down what a tree is and the different parts of a tree data structure. Trees, like linked lists, are made up of the same parts. Trees have nodes and links or edges that connect them. The first and most crucial part of any tree structure is the root. In fact, the node that we call the root node of a tree is really all you need to make a tree. But our tree can also grow in size. A root node can connect to other nodes in the tree. These are known as child nodes. The connection between a root node and its children is made through something called a link or an edge. Just as there are child nodes, there are parent nodes as well. A parent node is any node in a tree that has descendants from it. Here we have a node that is the child of the root, but also parent to two other nodes here. Just as you can have parent nodes and children nodes, it's also possible to have sibling nodes, like these two nodes down here. Sibling nodes share a common ancestral parent. Sometimes, however, a node in a tree might not have any children, like this one. If you think of the root node and all of the nodes branching out from it as branches, the end of a branch contains a leaf. That's what we call nodes without any children in the tree. Any node that is not a leaf node is what we call an internal node. Another way to think about it is any node that has a child and isn't a leaf will be an internal node. In this case, we have multiple internal nodes, like these two here. Even if the terms seem confusing at first, the most important thing to remember about tree structures is that they're not linear, that nodes can connect to nodes in different ways, but the most important of all being that the data has hierarchy. There's a fundamental truth to trees that has to do with the relationship and number of nodes as compared to the ratio of edges. We know that a tree can only ever have one single root node. A root node can never have anything linking to it. There's a rule for trees that says if you have n number of nodes, you will always have n minus 1 links or edges. If we look at this example, we have 3 nodes and we have 3 minus 1 edges. Let's add some nodes and make this tree more complex and see if this rule is still true. So we've added more nodes. And now we have 1, 2, 3, 4, 5, 6, 7, 8, 9 nodes. Let's see if we have 9 minus 1, 8 edges. If we count them, 1, 2, 3, 4, 5, 6, 7, 8, we'll see that this is indeed the case. The reason that we can prove this to be true is simply based on the fact that a root node can never have anything linking to it. A root node may have children of its own, but since it will never have a parent, we will always have one less edge than the number of nodes in the tree. Even if we know only the number of edges, we can figure out how many nodes the tree has. There's another interesting characteristic of trees, and this is the fact that they are recursive structures. All this means is that one single tree structure may actually contain many trees within it. The technical term for this is subtrees. In this example, we have a tree with a root node and multiple levels of children within it. If we just look at this one half of the tree, we'll see that this node, while a child of the root, is also parent to its own children. This entire section of the tree could be a tree in and of itself. And in fact, it is. Now, if we look at this one subtree and look at its children, we'll see that there is a subtree within our subtree. Here we have a child node of this parent node. This parent node is the root of this subtree, and this child node is the root of its own subtree right here. We can see that trees can contain nested subtrees within them, which is exactly what makes them recursive structures. Here's another way to visualize this same tree. The recursive aspect of trees ends up being pretty important when you want to run algorithms on a tree data structure. If you can count on the fact that subtrees can exist within larger trees, it makes it a lot easier to run search algorithms, since every tree, when it's large enough, will contain a subtree within it. It's really important to know the type of tree that we're dealing with. There are two important properties that help us classify and understand trees even further. Those two properties are the height and the depth of a tree and the nodes within it. Let's deal with depth first. We're generally concerned with depth in the context of a node. An easy way of understanding the depth of any given node is by answering the question, how far away is this node from the root of the tree? If we can determine how far away a node is from the root, we basically have found how deep that node is, or its depth, within the larger tree. Here's an example of a tree. Let's try and determine the depth of these highlighted nodes. We know that the depth of a node is how far away that node is from the root. An easy way of keeping track of how far one node is from the root is simply by relying on the edges. We can count the number of edges that we pass from the root to the node that we're trying to check. We can use that to determine how far away the node is from the root. Let's look at this orange node first. From the root, we pass one edge to reach this child orange node. The depth of this node is 1. But what about this pink node? We need to pass 2 edges to get here, so its depth is 2. Following the same logic, there are 3 edges that connect this red node to the root, so the depth of this node is 3. Height is a slightly more complicated property, but it helps if you think about the fact that a tree as a data structure is basically just the trees we see in nature, but flipped on its head. To understand the height of a tree, what we really need to do is answer the question, how far away is this node from its furthest away leaf? In other words, what's the branch height of this node that we're looking at? Let's look at the height of this orange node. Remember, the question we're trying to answer is, how far away is this node, counting with edges, from its furthest away leaf. If we look at this node and the leaves that it has, we know that it has one right here and 3 more here. Since we're looking for the leaf that is the furthest, we'll ignore this leaf for now. Let's consider these 3 leaves. They're all equidistant, they're all siblings, so it doesn't really matter which one we pick. They're equivalent in terms of leaves. Since these are the furthest away leaves, we can use the edges connecting these leaves to our node and count how long this branch is, because that's really what we're measuring when we're measuring the height of this node. If we count the number of edges from our node to its furthest away leaf, we'll see that there are 1, 2, and in all 3 situations, 3 edges that connect to the furthest away leaf. Thus, the height of this orange node is 3. Another interesting characteristic about trees has to do with the height of the entire tree. If you determine the height of the root node, you can basically answer the question, how far away is the furthest away leaf in this entire tree? In this example, the height of the root node is going to be 1 more than the height of its child. We can confirm that by looking at the root node's furthest away leaf. In this case, we'll see that there are 1, 2, 3, 4 links to the furthest away leaves. The height of the root node is 4. Because the root node is the single source and the origin of the entire tree, the height of the root node is effectively the height of the entire tree. The reason that height and depth are 2 crucial properties when understanding trees is because they give us insight into what our tree looks like. And sometimes we really care about what our tree looks like. Let's look at 2 examples. We'll look at a balanced tree and an unbalanced tree and try to understand how the 2 are different in the process. A tree is considered balanced if any 2 sibling subtrees do not differ in height by more than 1 level. On the other hand, if there are 2 subtrees that are siblings and their heights differ significantly, that is to say by more than 1 level, then they're considered unbalanced. Here is an example of a balanced tree. We'll see that there is a subtree here and a subtree here. Neither one of them differs in height by more than 1 level. Here is another tree with a subtree over here and a subtree over here. We can tell that the subtree on the right differs significantly in height, which is what makes it unbalanced. We'll come back to why exactly balanced trees are so important to think about in a moment. But before we do, let's look at a tree example in the wild. One example of a tree structure can be found in any object-oriented language. In many object-oriented languages, there will be subclasses and subcategories of object, all of which inherit from one larger version of object. That larger version, that uppermost class that all the other objects inherit from, is really just a root class, which is a root node in a tree. Subclasses of other classes are subtrees within a larger tree structure. If you think about the fact that object-oriented languages often refer to a class hierarchy, the hierarchical nature of a tree structure starts to become more obvious. The hierarchy of classes mirrors the hierarchy of nodes within a tree structure. Another example of trees that we all interact with are file systems. Here's an example of what your file system might look like on your machine. You probably, at some place or another on your desktop, have some sort of root directory. That root directory may contain a single file, but it's also likely that that root directory contains a subdirectory within it. Depending on how organized you are, you might have yet another subdirectory within that subdirectory, and that subdirectory may have many files within it. In particular, they're tree data structures, and they're all sitting on your desktop. Trees can be balanced or unbalanced, and they can exist in the most subtle places in our operating systems. But there's one kind of tree that's particularly interesting and can be really useful for running quick algorithms. One of the most commonly used forms of the tree data structure is something called a binary search tree, which is a type of tree but follows a very specific set of rules. However, those rules are what makes it so powerful. So let's understand where the binary in a binary search tree really comes from. When something is binary, we know that it means it has two parts. But a tree only has a single root node. So how does it have two parts? Well, you'll remember that trees are recursive data structures. They have trees within them, which we call subtrees. A binary search tree has two main subtrees within it, and that is in fact what makes it binary. Let's look at an example and see if we can unpack this a little bit further. Here we have a simple tree. It's balanced and it has two halves to it. We have a root node, which we know we must have, and that root node has two children. It has a left child and it also has a right child. Each of these children nodes are parents on their own. They have their own children nodes, which makes them subtrees. We can refer to this as the right subtree. Similarly, we can refer to the entire tree of the left child node as the left subtree. As a rule, every binary tree will contain these two subtrees within it, a left subtree and a right subtree. So now we know the two halves that make a binary search tree. But there's something else unique about binary search trees too. And this is part of what makes searching through them so powerful and efficient. Binary search trees must be sorted so that their nodes appear in a specific order. The general rule for the sorting of a binary search tree is something like this. Everything in the left subtree of the root node has to be smaller in value than whatever the root node is. Similarly, everything that is in the right subtree of the root node must be greater in value than the root node itself. This tends to make more sense with an example, so let's create our own binary search tree and understand how this sorting order works. Here's an example of a binary search tree where all of the nodes actually contain some data. This will help us see what the sorting order of a binary search tree actually is. Here we have the root node, which has a value of 26. You'll recall that in a binary search tree, all of the elements in the right subtree have to be greater in value than the root. All of these elements must be greater than the value of the root node. If we check, we can see that 33, 31, and 40 are all greater than 26. We'll also notice that in this subtree itself, the element to the right of this subtree's root, 33, is greater than 33. The rule of right subtree being greater applies not just to the entire binary tree, but to all of the subtrees within it. If the right subtree must always be greater in value, then it goes to say that the left subtree must be less in value than the root node. If we look at our left subtree here, we'll see that this is indeed the case. Again, notice here that the element in the left subtree of this blue subtree is less than 19. The right child of this subtree is greater than 19. No matter the size of our binary search tree and how many recursive subtrees it contains, it must always follow these two rules. Now, if we wanted to insert an element into this binary search tree, we could do that as long as we followed the rules while inserting. Let's say that we have a node with a value of 21. We'll compare it to our root node 26. Since 21 is less than 26, we know that the node 21 cannot be inserted into the right subtree at all. From the root node, we'll move down to its child. 21 is greater than 19. So we know that the node we're inserting cannot exist on the left side of this left subtree. It has to live somewhere down here. We'll move down again and compare 21 to 24. 21 is less than 24, so we know that we must insert 21 somewhere in the left subtree of 24. As it turns out, 24 doesn't have any children yet. We can easily insert our node 21 right here. Notice that we're not breaking any of the rules of a binary search tree. But we also did something else very interesting. Every single time we compared our node to the root node of one tree and then the subtree within it, we eliminated half of the choices of places we could insert our node. When we started at our root node, as soon as we knew that 21 is less than 26, we didn't even bother looking at this subtree at all. We eliminated 50% of the possibilities right then and there. This is the heart of something called binary search. Binary search trees leverage the power of the binary search algorithm. The binary search algorithm is one of the most effective and well-known ways of searching for an element in computer science. Formally, a binary search algorithm is an algorithm that divides and conquers data, making it easy to find an element in a large data set. Binary search simplifies and speeds up the process of searching by dividing one data set into half, binary, every single time it takes a step. Let's take a look at the divide and conquer technique in action using the same tree we had before, but rearranging it so that it becomes a bit more obvious how binary search is working. We're looking for the element 12, or the node 12 in our tree. You'll notice that our tree has just been rearranged here into a sequential order, but we're applying the same binary search algorithm technique. We'll start with the middle item, 26. You'll recall that 26 was our root node. Remember that everything to the left of 26 was our left subtree, and everything to the right of 26 was originally our right subtree. Because of the ordering of a binary search tree, we can reorder the nodes into a sequential series of elements, much like an array. We choose the middle element and compare the value that we're looking for with the value inside of it. Since we're looking for the node or the value of 12, we know that 12 is less than 26. We know that we can eliminate half of the values, all the values to the right of 26, since they will be greater than 26, and what we're looking for is less than 26. So we'll eliminate the entire right half of this structure and the node we were just looking at. Now we have just 3 items left. Remember, we started with 7, eliminated 4, and now we're left with 3. We're dividing the number of elements to check each time. With these 3 elements, we'll again check the middle item and compare it to the value we're looking for. Since 12 is not equal to 19, but is less than 19, we know that we can ignore the value to the right. If we ignore the value to the right of 19, all we have left to check is any values to the left of 19. Eventually, we arrive at the value we were looking for, the number 12. So you can see that binary search can be applied to a tree structure, but as we just saw, we can apply the same methodology to an array or any collection of items. The most important thing is that the items be sorted in an order. You'll remember that I said that balanced trees are pretty important to binary search and binary search trees. If you think about this deeply, you'll realize that an imbalanced tree, one with many more nodes on the right subtree than the left, for example, would mean that every single time you look at the root node, you would end up with one side of the tree heavily balanced with larger numbers than the other side. Binary search doesn't really work well or efficiently if your tree isn't balanced and you can't eliminate half of the values each time. It turns out binary search powers so many things that we interact with all the time. One of my favorite examples of this is a command in Git called git bisect. When you use git bisect, you can use the power of binary search to narrow down a commit that introduced a problem. Git bisect leans on us as programmers to tell it which commits are good and which ones are bad. It takes all of the commits in between and orders them chronologically. Git bisect picks the center commit, uses binary search, and allows you to search for regressions and problematic code that has been pushed in very few steps. Trees exist everywhere around us, as do binary search trees and binary search. I hope you understand and have a better appreciation for trees, and binary search now. Find the rest of my videos and articles at dev2/Vaidehi Joshi. Thanks for watching.